So hello everyone and welcome to the second day of the Lost Landscape of Neural Network workshop. We are very lucky to have Surya Ganguli today with us from the Department of Applied Physics at Stanford University, and he will talk to us about some recent results on the geometry of Lost Landscape. If you have any question, you can use the Q&A features of Zoom, and after the end of the talk, you will have 10 minutes for discussion. So Surya, you can start. Thank you so much.
Okay, great, thanks. So yeah, thanks for the invitation. This looks like a super fun workshop. So let's see. Okay, yeah, so there's lots of sort of intersections for math and physics and ML to inform each other, right? Understanding ML using techniques from math and physics, using ML to advance our understanding of complex systems. I'm going to talk about something slightly different today, which is implementing ML in devices with novel physics and using mathematics and physics to understand the relationship between dynamics and computation in these devices, especially understanding their high-dimensional sort of loss landscape geometry. So the kind of two topics I'll talk about are energy landscapes and annealing schedules in a dissipative many-body quantum optimizer. And if I have time, I'll mention a recent result on enhancing the capacity and robustness of hot field networks when they're implemented as associative memories using a confocal cavity quantum electrodynamics. Luckily, we can reason about these systems in their classical limit, and so we won't have to discuss the quantum aspects of it here. We've been spending a lot of time working on sort of using math and physics to try to understand deep learning. Here's some references. If you're interested in a review article, here's a review article we wrote recently that covered a whole bunch of topics, including sort of works on the error landscape of neural networks. Okay, so without further ado, let's get started. So what's the motivation for this dissipative optimizer? So it turns out that many optimization problems can be encoded in an Ising formulation, where you have a bunch of Ising spins, and you have some interconnections between them, some Jij connectivity matrix, and you're just trying to minimize energy of this set of Ising spins. So here's a nice review article in formulating sort of many combinatorial optimization problems, encoding the degrees of freedom to be optimized over in these problems as Ising spins, and encoding each problem as a particular choice of this connectivity matrix. So solving Ising problems is a very general way to formulate optimization problems. Okay, so then my colleagues in applied physics at Stanford built a many-body quantum optimizer to solve these Ising systems. So we don't need to go too deeply into the physics, but basically what they did is they hooked up a bunch of optical parametric oscillators that basically are oscillators that consist of the electromagnetic field oscillating in a certain mode. And you can hook up many of these oscillators, and you can set up a nonlinear oscillator such that the oscillator prefers two phases. These two phases could be considered spin up and spin down in an Ising model reduction of the dynamics. And you can set up interconnections between these oscillators using these optical fibers, okay? So, so this system can work in a deeply quantum regime. It can also work in a classical regime. And even in a relatively classical regime, it does pretty well in optimizing various things. And they've done various benchmarks. If you're interested in a recent review that I wrote with my colleagues, you can take a look at this article here. But again, I said we're not really trying to understand the quantum regime yet. We're just trying to understand why it works classically. So what's a good mathematical model for thinking about this machine? Well, consider the three following optimization problems. Okay, here's the original Ising optimization problem that we would like to solve. Okay, this is our fundamental goal here. Okay, oftentimes what machine learning people do is if they have a hard problem, they relax the problem by releasing some constraints. A common relaxation, a very easy relaxation, is the spectral relaxation. Instead of having the spins be binary, allow the spin vector to be just a general unit vector. And then minimizing this energy function is tantamount to finding the principal eigenvector of J. And then you can just round the elements of the principal eigenvectors of J, take their signs to recover a feasible point of this optimization problem. Okay, that's a reasonable way to attack it, but you don't often get the lowest energies possible in the original Ising problem using a spectral relaxation. What the icing machine does is but by the way, you have to power up the icing machine. So there's a pump beam, and the way you operate the system is you slowly crank up the laser power of the pump beam. Okay, what does that do physically to the energy function of the coherent icing machine? You could think of the coherent icing machine as having a set of soft spins, okay, that live in a single well potential. Each individual spin lives in a single well potential if this laser power, suitably renormalized as negative. But as you crank up the laser power, the single site potential for each spin becomes a double well potential. And you, of course, have the quadratic interactions coming from the optical fibers, okay? So basically what happens is this machine interpolates from the spectral relaxation, when you have a single well potential, to the icing energy function if this double well potential becomes very, very deep and very, very large A, okay? So there's this interpolation process. So you have a continuously changing energy landscape. And we'd like to understand, can you solve certain problems, i.e. get to lower energy in the icing system by deterministically annealing your energy landscape in this fashion, okay? We find numerically that we can. So what we did was we studied the Sherrington-Kirkpatrick spin glass as a prototypical example of an optimization problem. It's not necessarily the hardest optimization problem out there, but it's not a trivial one, okay? In the language of recent works, that this problem doesn't have an overlap gap, so that's why it's not an impossible problem to solve in polynomial time, we think, all right? So in any case, for going forward, we're not going to study general optimization problems. We're going to study the Sherrington-Kirkpatrick spin glass, where the Jij matrices are drawn as IID Gaussian elements with mean 0 and variance 1 over n. Okay, so we simulated the icing machine. We started, so we initialize the x's, the soft spins, randomly near the origin. We start at a small value of the laser pump power. We increase the pump power a small amount. We minimize the energy via gradient descent, and then we repeat. So we're always minimizing energy, and we're slowly changing the landscape. So the landscape goes from something that looks like this to a highly corrugated landscape over time. And we find that the icing energies that we find from the coherent icing machine get smaller and smaller as the system size gets larger and larger. And the known ground, so this is the intensive energy per spin. The known intensive energy of the Sherrington-Kirkpatrick spin glass is around minus 0.76. The known energy obtained by spectral relaxation is up here. And we see that the coherent icing machine is doing relatively well. It's much closer to the true ground state than the spectral relaxation. Okay, so the questions we'd like to ask are, what makes this possible? What is the shape of the energy landscape? How does it change with the laser pump power? And how can we exploit our understanding of this changing geometry to determine the optimal annealing schedule of how you should increase A, the laser pump power, with time? In fact, we actually answered all these questions and found the optimal annealing schedule, and this is how we got this result. So I'm kind of showing you the final result before I explain how we got it, okay? Okay, so to do this, we conjecture, of course, that the geometry of the energy landscape is very important to understanding why you can get to low energy. To think about the geometry of high-dimensional error landscapes, these cartoon pictures that we keep in mind are woefully inadequate for thinking about what's going on in high dimensions. So, a common way to think about the geometry of error landscapes is to consider all the critical points where the gradient of the energy or loss or error vanishes. And think about where these points might sit in a two-dimensional feature space, where one feature is the error or energy level, right, on the horizontal axis, and the other feature is the fraction of negative eigenvalues of the Hessian. So how many negative curvature directions do you have? And classical work by Bray and Dean on random Gaussian landscapes suggests that for at least these random Gaussian landscapes, there's a strong correlation between the error level and the index, so the fraction of negative eigenvalues of the Hessian. So, here's the global maximum. You're at the highest error and all the eigenvalues of the Hessian are negative. Here's a typical local minimum. You're at the bottom, near the bottom of the landscape, and all the eigenvalues of the Hessian are positive. And as you go up in error, you get saddle points of increasing index. And the global minimum might be even a little bit lower than the energy level of the typical local minimum. Okay, so this was sort of worked out by Bray and Dean, and we'd like to try to understand this for the coherent Ising machine. By the way, in some old work, that I've already talked about a while ago, we showed that this correlation between index and error level actually holds in the energy landscape of deep neural networks. And if you're interested in the details, you can find them in this paper from a while ago. We see the same correlation. This implies that sort of local minima at high error, at least statistically by the methods that we use to search for them, basically Newton's method, are hard to find. Okay, so now let's go back to this coherent Ising machine. Okay, so the specific questions that we like to ask are, as a function of the coherent Ising machine energy, the radial distance from the origin, and the laser pump power, where does the global minimum lie? Where do the most likely local minima lie? Where do the most likely saddle points of a given index lie? And given a critical point, what is the distribution of soft spins, xi here? And what is the eigenvalue spectrum, the Hessian, of a critical point as a function of its index, energy, and radius? We'll be able to answer all of these questions analytically and confirm our analytic results with numerical simulations. But let me give you the take-home message of what's going on. So here's a cartoon picture of of our analytic results. So if you start at very, very large A, where the landscape should be quite corrugated as in here, as opposed to small a, where it's sort of quadratic, or convex at least, what you find is you find this picture for the energy landscape. The global minimum is far out in radius. So this horizontal plane is a stand-in for n-dimensional X space. Okay, this vertical axis is the energy. So the global minimum sits somewhere far out in radius, and it has the lowest energy. There can be exponentially many local minima that sit at a little bit higher energy, and then you get saddle points at higher energy and smaller radius and higher index. Okay, so that's the picture of the landscape. So if you optimize just starting at large A, you get a hard optimization problem where it can be difficult to penetrate this wall of typical local minima to get to the global minimum. However, if you look at smaller A, you get this similar picture, but the entire shell is concentrically expanding. So you can surf the surface of the shell and get to energy levels through deterministic annealing that are much lower than the energy level of typical local minimum. Okay, that's kind of the take-home message. So let me justify that message now. Okay, so what are the theoretical techniques that we use to calculate all of this? Well, the fundamental thing that we're interested in computing is the complexity, which is basically you sum over all of the critical points, okay, at any point where the gradient of the energy vanishes. You constrain the energy of the critical point to equal some intensive energy, so alpha indexes critical points. You constrain the index to equal some intensive index. You can also and then you can just compute the logarithm of the number of critical points. Okay, so we'd like to compute the complexity of critical points as a function of their energy and index. We can also introduce an additional delta function to compute them as a function of their radius. Okay. How do we calculate this complexity? We can compute instead this grand potential, and we can calculate this grand potential using the Koch-Rice formula, the replica method, and supersymmetric methods, actually. And then the complexity is the Legendre transform with respect to the effective inverse temperature and chemical potential, and you get this complexity. So I'm going to skip all of the details of this, but I'll just mention, why is there supersymmetry? When you try to plug in the Koch-Rice formula for counting critical points, the determinant of the Hessian shows up in the Koch-Rice formula. And you can express the determinant of the Hessian as an integral over some fermionic variables. And there's other terms in this Koch-Rice formula that represent bosonic variables. So this grand canonical potential can be expressed as an integral over bosonic and fermionic variables. This integral has supersymmetry that exchanges the bosonic and fermionic variables. And the solutions that you find to the saddle point solutions that you find to this integral can either respect the supersymmetry or break the supersymmetry. And also you have to introduce replicas. So the saddle point solutions can either break the replica symmetry or preserve the replica symmetry. So there's different types of solutions with broken or unbroken replica symmetry and broken and unbroken supersymmetry, and they have different physical meanings. I know that was a mouthful because if you're not familiar with this stuff, I know that made no sense. But for the aficionados, I just wanted to state the techniques that we used. Okay. All right. So now let's get to results. So this justifies this concentric ring structure at large A. Okay, so what we did was we numerically simulated the system for the size that we could do, n equals 15, where we could relatively exhaustively count all the critical points of any index. Okay, this heat map shows all the critical points that we found numerically in the numerics. Okay, this horizontal axis is the energy, and this is the radius. Okay. And you can see that as you go down in energy, you go out in radius, okay? Then we took the mean of all of the critical points in this two-dimensional feature space constrained to have a given index. And the low index ones sit over here at low energy and large radius. So that's the stuff down here at large radius. And the high index ones sit here. And the red line is our theoretical calculation of where these things should sit. Where should the most likely critical point of a given index sit in energy and radius space? And as you can see, there's a nice match between theory and experiment. So this is a theoretical justification for this cartoon picture here. Okay, so this is at large A. Okay, now what happens at small a and as you increase A, the laser pump power? Okay, so yeah, so we can do more than just compute the complexity. We can actually compute the histograms of Xi and the Hessian eigenspectrum at every value of A. Okay, so here the blue histograms are from numerical simulations of the system. We just numerically search for critical points. We numerically search for local minima, and we also exhaustively search for the global minimum for systems, for small system sizes of n equals 15 or so. And then the orange curves are what we compute from our theory, okay? And you can see there's a very nice match between theory and experiment. And as you can see, as you increase A, the distribution of spins in a typical local minimum at small a, they're relatively uncommitted and there's some positive density at the origin. As you increase the laser pump powers, the wells become deeper and deeper. They commit to positive and negative values. And the Hessian eigenspectrum looks like this. Typical local minima are only marginally stable. By marginally stable, I mean the Hessian spectrum extends all the way to zero. It vanishes at zero, but it does extend all the way to zero. So that means zero eigenvalues, the Hessian means very, very flat directions, which the system is very sensitive to external perturbations. So this is typical in many high dimensional systems where a randomly chosen local minimum will be marginally stable in this fashion. We can also compute the statistics of the global minimum. And as you can see in the global minimum, the spins are even more committed to their positive and negative values than they are at a typical local minimum. And the Hessian eigenspectrum undergoes a phase transition where at small a, it's marginally stable, but at large a, there's a gap in the spectrum between zero and the smallest eigenvalue. So now the system becomes stiff, right? Every single dimension is protected by positive curvature of the Hessian. So it's stiff, it's relatively resistant to external perturbations, okay? All right, so what does this mean sort of for the phase diagram, okay? So now because we can also compute the energies of the local minima, the global minimum, the radius, all of that stuff. And so I can summarize the results in this following picture. So this is roughly the phase diagram of the energy landscape as you increase A, okay? If A is negative, remember the types of solutions that we find can be characterized by broken or unbroken replica symmetry and broken or unbroken supersymmetry. Okay, for A less than -2, which is the minimum eigenvalue of the J matrix, if J is a random Gaussian, you have replica symmetry and supersymmetry, and there's just a single stable local minimum. So over here, there's no action going on, right? There's no double well potential. There's a global minimum at the origin. If you increase A a little bit, okay, you start to get a double well potential, and there's many local minima, but they all have very, very similar energy densities, okay, energy per spin. And all of them are marginally stable. And in fact, the global minimum has the same intensive energy as the local minimum, right? Of course, there are extensive energy differences when you multiply the intensive energy by n, could have differences that are order 1. But as far as the energy density goes, global minima and local minima have the same energy density, and it's very, very flat. All of the local minima are marginally stable. The Hessian and you can see that right here, right? The Hessian of the global minimum and the local minimum are similar, okay? All right, as you crank up A even further, there's a phase transition in the landscape where the local, you now have exponentially many local minima. The local minima are marginally stable. The global minima is marginally stable also, but now there's a range of energies for the minima, right? There's this range of energies out here where the global minimum now starts to have lower energy than a typically chosen local minimum, okay? So that's this setting. And this is supersymmetry is broken here. Now, for the aficionados, a question is, what's the physical meaning of supersymmetry breaking? We can show that the order parameters for supersymmetry breaking using a cavity method basically relate to how structurally stable the landscape is to the addition of an external spin. So we have a geometric interpretation of the supersymmetry order breaking parameters, but that's a technical result. Now, at this, there's a freezing transition at a larger value of A where the global minimum is no longer marginally stable and is fully stable, okay? So this is the picture here. Now, there's still a separation between the global minimum and the local minima, but the global minimum is now sharp. It's no longer flat as it is here. And the whole system freezes. If you're in the global minimum and you crank up A, there'll be no changes in the signs of the spins at least, okay? What are these curves? So these curves are the blue curve is the energy of a typical critical point, okay? So this means a critical point of any index, that'll always be higher energy than the local minimum or the global minimum. The orange curve is the energy of the typical minima, and the green curve is the energy of the global minimum. As you can see here, as promised, all three have the same energy. So that means all critical points have intensive index 0, okay? Then there's a separation between the global minimum and the local minimum. The curves are from analytic theory, and the points are from simulations. And you can see there's a nice match between theory and simulation, okay? Now, what does this mean for optimization, okay? Why is it that we can find very low energies? Okay, so if you think about a cartoon version of the picture that I showed you, right? At small a, all the local minima and the global minimum all sit at the same radius and the same energy. And there may be very, very low index saddles where the intensive index of the saddle is still 0. The extensive index, the actual number of negative eigenvalues may be order 1. So it's a relatively easy landscape. It's easy to get to the outer edge at small a, right? As you increase A, the global minimum separates from the local minima, and then it eventually freezes, right? So the picture of the deterministic annealing process is that as as you're changing the landscape, you're also doing gradient descent on the landscape. So you immediately get to the outer shell, and then you expand the shell. So you're always surfing the outer shell of this onion, and you can actually get to CIM energies that are much lower than the energies of the typical local minima. And that's the evidence for that is this plot, okay? So as you increase A, this is the energy of typical local minima. The blue is the energy of the global minimum, the analytic theory. And the red is the energy of what we find using adiabatic annealing, right? Where we increase A, do gradient descent, increase A, do gradient descent, and so forth. And you can see that adiabatic annealing follows the energy of the global minimum, not the energy of the typical local minimum, which is higher. Okay, this also tells us what the optimal annealing schedule is. Okay, so this plot is telling you the energy that I find relative to the ground state energy for different for annealing to a particular maximum value of A and different speeds of annealing, where higher in energy is higher speeds of annealing. And it turns out that the optimal thing to do is to anneal slowly until you get to the freezing transition. And then you get the lowest energy, right? If you anneal to a larger value of A and you blow past the freezing transition, you have a chance of not settling into the outer shell, the global minimum of the outer shell, and you blow past it and you get trapped at a higher energy level. You're still lower than the energy level of typical local minima, but you're trapped at a higher energy level. Okay, so this illustrates a connection between geometry, dynamics, and computation, right? In the sense that the landscape geometry tells you there's no point in annealing beyond the freezing transition, and you want to go relatively slowly up to the freezing transition, but you don't need to go that slowly. Okay. And this is now the icing energy. Okay, so I've been talking about the coherent icing machine energy, the thing that you can think of this as a training error landscape. This is a test error landscape where it's a different energy function, the one that we actually care about minimizing. And as you can see, the optimal icing energy that we achieve occurs around here, where we anneal up to the freezing transition and we go as slow as possible. If you anneal up to the freezing transition, the speed of annealing doesn't really matter. But if you anneal up to a larger value of A, the speed of annealing matters, where if you do fast annealing, you do much worse. If you do slow annealing, you do better, but not as well as slow annealing up to the freezing transition. Okay, and so this was the annealing schedule that we used to show you the nice results at the beginning of the talk. Right. There's lots of interesting directions to go here. For example, you can make the forces non-conservative. You can make J asymmetric. Then there's no longer an energy function, but there is a dynamical system. And just as we were able to count the critical points of an energy landscape and compute the spectrum of the Hessian, there are techniques to, also using the Catch-Rice formula to try to compute the fixed points of a dynamical system that doesn't obey an energy function, and also compute the spectrum of the Jacobian, i.e. the stability of the fixed points. So that's an interesting direction that we're thinking about at the moment. There's an entire universe of optimization problems. We just looked at one optimization problem, the Sherrington-Kirkpatrick spin glass, but there's this entire universe of optimization problems that can be mapped to icing systems. And, it could be an entire career to work out energy landscapes for this thing. I don't think I'm betting my career on that. I have other interests, but there is a career that could be made out of this. We are working on some of these in collaboration with other people. By the way, there's a nice connection between the dynamics of this coherent icing, a qualitative, not quantitative connection between the dynamics of this icing system and survey and belief propagation. And if you're interested in that review, if you're interested in kind of an overview of that connection, you can check out this review article. And this opens the question, right? In other areas of artificial intelligence, have we not really exploited deterministic annealing of a broader class of hyperparameters? For example, could we anneal the nonlinearity? Could we anneal, we're always annealing learning rates and we're annealing all sorts of stuff, but can we anneal other aspects of the architecture? Maybe there's other interesting things to explore there in the context of these systems. So I will skip this hot field networks and cavity quantum electrodynamics, but luckily that work is published. So you can read about it if you're interested. There, we also had very interesting energy landscapes, and the quantum dynamics yields a very different way to traverse the energy landscape that does better than Gibbs sampling. That's kind of the take-home message. So, the impact of an energy landscape on learning and computation depends not only on the shape of the landscape, but it depends crucially on the dynamics that you use to traverse that shape. And here we showed that by keeping the same shape, but changing the dynamics going from classical to quantum, we could increase the size of the basins of attraction of energy minima in the hot field model. That's kind of the take-home message here. Again, that's published. The first part of the talk is not published, but a draft should be on the archive pretty soon, in probably a month or so. Okay, so let me skip that, and yeah, I'll stop there. Okay, thanks.
Cool. Thank you so much, Surya. That was really, really interesting. If you have any question, you can use the Q&A features, and I think we will start by Clément. Clément?
Yeah, so thank you for the inspiring talk. I have a question. I mean, somehow, so you explained that if we increase the parameter A while doing gradient descent, we can find this much lower minimum. But in order to do this, you use the analytical knowledge that you gained through your analysis about the landscape to actually know how you're going to, I mean, to know in which phase you actually are at any value of A.
Yeah, I mean,
we have a problem where we don't really know where we are, right? So we'd like still to kind of increase the parameter while doing gradient descent. Is there a way to kind of get the sense of where we are without having this analytical background?
Yeah, you can do it by brute force, right? The space of annealing schedules is a 2-parameter space, right? You choose what's the maximum A that you're willing to go to. So A max is 1 parameter.
Okay.
And then we just linearly increase A over time. So the slope of that rise is another parameter. You can do a brute force exploration of this 2-parameter space and record the minimal icing energy. You can record the icing energy and the CIM energy you get as a function of this 2-parameter space. And we could have done that actually from the beginning, right? And then we would have found, so for example, that's exactly what we did in this exploration. So this axis is A max, and the color axis is the speed of annealing, right? And so we could have just done this without any theory, and we would have found the best solution is here. What the theory is adding is that the place of the best solution is occurring at the freezing transition, right? So yeah, so in that sense, you could have gotten this result with no theory at all, but you wouldn't have understood why, right?
Sure. Okay, thanks.
Giovanni?
Yeah, thanks. It was very interesting. I can guess roughly how you get those results when you assume that coupling strengths are normally distributed.
Yeah.
Now, I guess in the Ising formulation of many MP problems, this condition is actually not satisfied. And I'm wondering, yeah, can you say some words about how to extend the results that you have here to those cases where the couplings are not normally distributed?
Yeah, I think that will be tough, right? There's some problems like number partitioning problems where this could be applied. This basically boils down to the fact that we really don't understand that much about spin glasses other than the mean field limit. So if you have some statistical ensemble of optimization problems that, you know, have local structure or things like that. I mean, the other place that we understand things are tree structured systems like beta lattices and things like that. It's a major open problem to pick a specific optimization problem that doesn't have a well-defined ensemble and understand its energy landscape. Yeah, it's a good question, and it's a very, very hard question that we as a community don't know the answer to. That's part of the reason that we first started with a shared Kirkpatrick spin glass, right? Because we could really understand the landscape there.
Berfin?
Thanks for the great talk. There's one question that I'm always confused about, the saddles in general. And in statistical physics, it's always emphasized the index of the saddle. But I know in non-convex optimization community, it is what matters is the minimal eigenvalue of the saddle, because that determines whether you can escape or not.
Yeah.
I would like to hear your take on this.
Yeah. The index is just a convenient way to classify the critical points, right? But we were actually interested in the entire Hessian eigenspectrum. I agree, the entire Hessian eigenspectrum contains a lot more information than the index, right? So actually, we also have the entire Hessian eigenspectrum for typical critical points, which I didn't show you. So this is for the typical minima and the global minima. So the index is 0, but the shape of the eigenspectrum changes continuously as you increase A, right, for both. For the typical critical points, where you just choose a random critical point of any index, you don't constrain the index, you of course get negative eigenvalues. And there's an interesting bimodal structure where you have some positive eigenvalues that are much of negative eigenvalues, and the density sort of vanishes near the origin. It pops out from our analytic calculations and is confirmed by numerics. And we don't quite, we don't have an intuitive explanation for why the density of the Hessian comes close to 0 near the origin for a typical critical point. but I completely agree with you. We would like to get as detailed information about the Hessian as possible. And we have that here for this problem, at least.
Giulio?
Hi, Surya.
Oh, hi, Giulio.
I have a question. I mean, a couple of questions are quite technical because I'm intrigued by the computation. So in the computation of the minima, so in the regime in which you have all the minima at the same height, so in that case you do the full replica symmetry breaking computation to get the minima in that region.
Yeah, we have to actually. What we do there is we actually do an annealed approximation, but we break supersymmetry. So basically, we don't break replica symmetry, but we break supersymmetry. And I was just discussing this with Atsushi yesterday, actually, is why don't we need to break replica symmetry there? And we don't, I mean, the only confirmation of why it's reasonably correct is this match between theory and simulation, right? So like these curves, right? We're at least getting the energies correct. Yeah. At that level.
And so, indeed, so that's impressive indeed. And so in the case in which you have exponentially many local minima, so
so here's actually, this is something I was just discussing yesterday, as we're writing this up. We actually don't have exponentially many minima here.
Yeah,
we have sub-exponential minima because the complexity is 0, right? So we have a sub-exponential number of minima, but we don't know what the leading term in that sub-exponential growth with n is, right? So actually, I have a question for you. Does so eventually we have to do full replica symmetry breaking here for the global minima. Now, does full replica symmetry breaking always imply exponentially many minima, or can you have sub-exponential minima with full replica symmetry breaking?
Well, that's a good question. I think you can have sub-exponential minima, but it's something that it's easy. I mean, it's complicated because one should do a quench computation, not an anneal one, and have everything under control. But yeah, I agree. So just sorry, if I can, just an initial question to the figure. So how do you? So in this case, so when you compare the analytics to the numerics, so for example, the yellow line. So these are the highest marginally stable minima that you compare to what you get from the dynamics. Or
so what we do is we look at relatively small systems of size n equals 15. We randomly initialize the x's and we do gradient descent many times, right? Until we stop finding new minima. And then what we do is we also find saddle points of higher index, but what we do is we just randomly pick one of the minima that we find, and then we compute the mean energy across a randomly chosen minimum. So the global minimum could be chosen, but it's exponentially, I mean, states of lower energy are exponentially rarer than the typical local minima of, the typical local minima are at the highest energy of all the minima.
Very nice. Thank you.
Wolfram, we have time for a last one.
Yeah, Julia, I studied your paper with Benarus on the p-spin spherical model with the ferromagnetic. It was very nice. So that's your paper is a model for how we want to write our paper. But we didn't have to do the quenched computations to get these results. So we should talk more offline. It'd be fun.
Sorry, thanks a lot for this really inspiring talk. And just to come back, so basically, I would like you to speculate about how this could relate to neural networks. And one point also in view of Pershing's talk yesterday is that in neural networks, you have the additional permutation symmetries that make that there you are guaranteed to have sort of these marginally stable critical points that have eigenvalue 0 because you have the extra redundancy. And so in that context, what can I learn? Sort of how can I connect?
So I think the case. So I'm gonna do the dangerous thing of showing you my let's see. We have a recent paper at iClear, which I have to, yeah, how many degrees of freedom do we need to train neural networks? So I should have actually mentioned this paper also. I think the picture in deep neural networks is very different because we're highly over-parameterized, right? So if you think about the loss sub-level set of some low loss, that's an extremely high-dimensional object in this space, right? And so because of the over-parameterization, I mean, the permutation symmetry contributes to it, but the over-parameterization, I think, is a stronger contributor. And so what that allows you to do is it allows you to train in a much lower dimensional subspace and still hit that low loss sublevel set, right? And so we were able to use results from high dimensional geometry to actually measure the effective dimension of this loss sublevel set. And we found that it's incredibly huge. Like the codimension of this loss sublevel set is very small, like for CFAR 10 type problems with reasonable architectures, the codimension is maybe, order of magnitude hundreds, right? Where you might have hundreds of thousands of parameters for CFAR 10, right? So basically you have so many parameters, but the loss sublevel set is almost as high as the number of parameters you have, which is probably why it's easy to optimize. It's easier to optimize in a random subspace. And there's some very nice theorems that we use from high dimensional geometry to measure this stuff. And there's nice phase transitions and all that stuff. So if you're interested, I would take a look at this paper, which is going to appear at iClear.
Thanks a lot.